Matrices are machines. They transform space, they stretch, they shear, and they rotate. When we apply a matrix to a typical vector, it gets knocked off. It changes its direction completely. Data is often messy and hard to read. But if you look at it from the right angle, the pattern becomes obvious. Eigenvectors are simply the mathematically perfect angle to look at your data. Among all the chaos of transformation, there are special, rare vectors that refuse to be knocked off. They might get stretched, they might get squashed, but they do not rotate. They stay locked on their original span. These are the eigenvectors, and finding them isn't just a math exercise. It is the key to unlock the hidden structure of your data. This is the secret behind Google's PageRank and the foundation of principal component analysis. Welcome to Decoding Complexities. I'm Pradeep. Let's decode the name. Eigen is German for own or characteristic. These are the matrix's own internal axes. Let's look at the famous equation. On the left, we multiply a vector v by a matrix A. Usually, this rotation changes the vector. But for an eigenvector, the result is exactly the same as just multiplying the vector by a single number, a scalar, which we call lambda. Here, v is the eigenvector representing the direction, lambda is the eigenvalue representing scaling factor. Think of eigenvalue as the volume knob or the energy level of that vector. If eigenvalue is high, the direction matters a lot. That's the signal. And if eigenvalue is low or near zero, the direction is mostly noise. The matrix acts like a scalar. It just stretches the vector. This looks neat, but how do we find them? We have two unknowns, v and lambda. To solve this, we rearrange the equation. We move everything to the left. We use the identity matrix I to make the dimensions match. Now, here is the key insight. For a matrix to squash a non-zero vector v into 0, the matrix must be singular, meaning its determinant must be 0. Let's solve this for a 2 by 2 matrix A. We subtract lambda from the diagonal. Now we calculate the determinant. We end up with a simple quadratic equation. We can factor this easily. So our eigenvalues are 5 and 2. These are the magic numbers. In these two specific directions, our matrix acts as a scalar multiplier of 5 and 2. But in production, we don't calculate determinants by hand. We use the optimized linear algebra library. We feed our matrix into NumPy's linear algebra EIZ method, and it gives us the same eigenvalues, 5 and 2. One thing to remember here is that NumPy does not always sort these for us. In machine learning, we usually care about the largest eigenvalues. So, we often need to sort this array immediately after calculating it. Seeing the numbers is one thing. Seeing the geometry is what makes it click. Let's visualize what happens to these specific vectors when we apply matrix A. On the left, look at a random red vector. When we apply the transformation, it rotates. It gets knocked off its path. Now, look at the blue vector, our eigenvector. When we apply the transformation, it stays perfectly aligned. It just gets longer. The direction is invariant. This vector is the hidden axis of the matrix. So, we have decoded the DNA of the matrix. We found the vectors that don't rotate and the values that tell us how much they stretch. But why does this matter for machine learning? Think about a massive dataset with 1000 noisy features. If we can find the eigenvectors of that data, we effectively find the main axis, the direction where the data contains the most information. This allows us to separate the signal from the noise. This is the math behind principal component analysis, and this is exactly what we will build in the next video. Check out the description for the companion blog post and collab notebook to visualize this transformation yourself. Hit that like button and subscribe as we continue to decode complexities of machine learning. Thank you for watching, and I will see you in the next one.